12.3 Lesson 1 Velocity and Acceleration. The objectives for today's lesson are: given a vector-valued function for the position of a particle moving in the xy plane, you will be able to find vector-valued functions for the particle's velocity and acceleration, and a real-valued function for the particle's speed. Vocabulary: position vector, velocity vector, acceleration vector, and speed. Remember that velocity and acceleration are vector quantities because they have both direction and magnitude, whereas speed is a scalar quantity because it only has magnitude. So that's why we have a real valued function for the speed and vector valued functions for velocity and acceleration. Consider this problem from Calculus AB: motion along a line. For example, motion along the x-axis. So you see the x-axis here, and we have in words, let x of t represent the position of a particle moving along the x-axis. So now, if you want to find the position of the particle at time t, then you will have t, comma, x of t. And if you want to find the position of the particle a little bit later, you'll have t plus delta t, signifying a change in time, and the position of the object at the new time, t plus delta t. Now, if you'd like to see the change in position of the object on the time interval from t to t plus delta t, then you're going to subtract the positions of the object. So the position of the object at the later time t plus delta t minus the position of the object at time t. So this is the change in position divided by the change in time. The later time is t plus delta t minus the first time is t. So when you simplify, t minus t is 0, just leaving you with delta t. This is what we call a difference quotient, and this would give you the change in position, which would be measured in units or perhaps feet if the units on the x-axis are measured in feet or centimeters, etc., divided by the change in time. Perhaps time is measured in seconds. So it could be units per second or feet per second, centimeters per second, etc. But this difference quotient gives you an average velocity on the time interval from t to t plus delta t. Now we, in Calculus AB, defined the limit of this difference quotient as delta t approached 0 to give us the instantaneous velocity of the object at a particular instant in time t. And this was our velocity function by definition. So this was our velocity function, v of t. And if you take a look at this, we have the limit of a difference quotient as delta t approaches 0, and it fits the definition of the derivative of a function that we learned in Calculus AB. So that is why the velocity is the derivative of the position function x of t. And you can apply this reasoning to understand that since acceleration is the rate of change of velocity with respect to time, you can have average acceleration on a time interval, and when you take the limit of the difference quotient giving you the average acceleration on a time interval, as the length of the time interval approaches 0, that gives you the instantaneous acceleration at time t. So what I wanted to show you here is that acceleration is the derivative of the velocity and therefore the second derivative of the position function. So we just reviewed some things that we learned in Calculus AB where we had a particle moving along a line. Today we'd like to go over the same concepts that we just reviewed, but for a particle moving in a two-dimensional plane. For example, the xy plane. So it's the same concepts, but applied to motion in a two-dimensional plane. So we will have a position vector telling us where the object is at a particular instant in time, and we'd like to think about how we can get the velocity and the acceleration vectors from the position vector, and how we can also get the speed function. So now we consider motion in a plane. So we have a vector-valued function, r of t, giving us the position of a particle moving in the xy plane. And if you look at this vector-valued function, it has a horizontal component and a vertical component, each multiplied by their respective standard unit vectors. So the next question that we have is, this is the position of the object at time t. R of t plus delta t would give us the position of the object at a later time t plus delta t. And if we subtract from that the position of the object at time t, this would give us the change in position of the object on the time interval from t to t plus delta t. So we may represent this quantity here as delta r. And if we divide the change in position by the change in time, which would be t plus delta t minus t, which of course simplifies to just delta t, then we would have the average velocity, the two-dimensional equivalent of the average velocity concept that you learned in calculus AB. Change in position divided by the change in time. To visualize what we have here, this difference quotient, let's take a look at page 848 from your textbook, and you can see here the vector r of t representing the position of our object at time t, and you can see here the vector r of t plus delta t representing the position of the object at a later time t plus delta t. So delta r would be the difference in these two positions, represented here by the vector delta r. In other words, how much did the object move as we went from t is equal to t is equal to t plus delta t. In this diagram, you can see that it moved to the right and it moved down. So what you have here is a difference quotient. You have delta r over delta t, giving you the average velocity on the time interval from t to t plus delta t. Now what happens as the length of time approaches, the length of the time interval approaches 0? What happens as the length of the time interval delta t approaches 0? Let's look at the second diagram here. You can see from the second diagram that as the change in time approaches 0, the position of the object at the later time, of course, approaches the position of the object at the initial time. And the change in the position becomes less and less. And what happens is this. We know from calculus AB that this particular difference quotient, the equivalent of this particular difference quotient, gave us an average velocity, and when you took the limit of that difference quotient as the length of the time interval approached 0, you got the instantaneous velocity at time t. So in the case of two-dimensional motion, what happens is as the length of the time interval approaches 0, this vector representing the change in position starts to approach the vector representing the instantaneous rate of change in position with respect to time at a particular time, or the instantaneous velocity vector at time t. And that is represented in the second diagram, and here is the vector representing the instantaneous velocity of the object at time t. And of course, because we are now moving in 2 dimensions, our vector has both direction and magnitude. The magnitude of the vector will in fact give us the speed of the object at that particular instant in time, and the direction of course tells us the direction that the object is going at that particular instant in time. So the limit of this difference quotient gives us the instantaneous velocity of the object at a particular time, and it is a vector because we're taking the derivative of a vector-valued function. As you can see from this definition of the derivative of a vector-valued function from the previous section, that's what we're about to do right now when we're about to take the limit of this difference quotient as delta t approaches 0 to get the velocity vector. And this limit is, of course, by definition, it is the derivative of the position vector r of t, which will give us, as we discussed now, the velocity vector at a particular instant in time. And of course, you can extend our discussion to go to acceleration. Acceleration is, as we learned in Calculus AB, it is the derivative of the velocity function, and we have the same here in 2 dimensions. The acceleration vector, this is the velocity vector. The acceleration vector is the derivative of the velocity vector, and it is the second derivative of the position vector. In the previous section, 12.2, we learned how to find the derivatives of vector-valued functions. So if you have a vector-valued function r of t, how do you find the derivative of that vector-valued function? You're going to differentiate each of the real-valued component functions with respect to t and multiply by their respective standard unit vectors I and j. So we're going to see that when we apply this concept to position vectors to get velocity vectors. So here we have the definitions of velocity and acceleration for an object moving in the xy plane. So we have to begin by looking at the position function, which is also a vector-valued function. It has 2 components. There is a horizontal component, or the x component of the position, and there is also the vertical component, or the y component of the position. So r of t gives us the position of an object moving in the xy plane. For example, you could have this particular position function, r of t is equal to ti plus t squared j, and the position of the object at time is equal to 2 would be 2i plus 4j. And when you graph this vector-valued function, it will give you where the object is at different times, and the object is traveling along a parabolic path. So at time is equal to -2, the position of the object is -2, 4. At time is equal to -1, the position of the object is -1, 1. At time is equal to 0, the position of the object is 0, 0. So this is how the object is moving in the xy plane. And this would be the direction of motion. So what is this definition telling us? It's summarizing the concepts that we've been discussing, and it's telling us that if you have x and y are twice differentiable functions of t. And what do x and y refer to? They refer to the component functions. So in my example here, I would have x of t is equal to t, giving us the x coordinates of the object's position at different times t, and y of t is equal to t squared, giving us the y coordinates of the object's position at different times t. So that's what x and y are. If x and y are twice differentiable functions of t, and r is a vector-valued function given by r of t is equal to x of ti plus y of tj, then the velocity vector, the acceleration vector, and speed at time t are as follows. So let's take a look at these definitions. It's simply stating what we'd already discussed, that the velocity is the derivative of the position vector. And how do you find the derivative of a vector-valued function? You're going to differentiate on a component-by-component basis. So you're going to find the derivative of the x component of the position function, multiply by the standard unit vector I, and add to that the derivative of the y component of the position function, and multiply by the standard unit vector j. And the acceleration is, of course, the derivative of the velocity vector, or the second derivative of the position vector. So you have x double prime of t, where x of t represents the x position of the object at time t, multiplied by the standard unit vector I, plus y double prime of t multiplied by the standard unit vector j. And we remember our discussion conceptually that speed is the magnitude of the velocity. So how do you find the speed of the object at a time t? You have to start with the velocity vector, and you have to find the magnitude of the velocity vector. And of course, the velocity vector is the derivative of the position vector. So you have to find the magnitude of the derivative of the position vector. And how do you do that? How do you find the magnitude of a vector? When we started this chapter, we learned that the magnitude of a vector v may be found by taking the square root of the sum of the squares of the individual components. And that's what we're doing here to find the speed function, which is a real valued or a scalar function. It's not a vector. Speed is a scalar. And it is the magnitude of the velocity function. It is the magnitude of the velocity vector. So you have the square root of, just like we had from the formula from the beginning of chapter 12, we have the square root of the sum of the squares of the x and the y components of the velocity vector. So let's go ahead and apply what we just learned to our example of the object moving along the parabolic path given by the position vector function r of t is equal to ti plus t squared j. So the individual component functions are x of t is equal to t and y of t is equal to t squared. And now we're going to go ahead and find the velocity vector. So the velocity vector is the derivative of the position vector, and you're going to take the derivative on a component-by-component basis. The derivative of the x component function, the derivative of t with respect to t is 1, so I will have 1i. And the derivative of t squared with respect to t is 2t, so I'll have 2tj. And if I wanted to find the velocity vector at a particular instant in time, for example, at time is equal to 2, I will just evaluate my velocity vector function at t is equal to 2 and get 1i plus 2 times 1 is 2j. And in fact, I can sketch this velocity vector at the point corresponding to the object's position at time is equal to 2. Where is the object at time is equal to 2? It's right here. And the velocity vector at that time has a horizontal component of 1 and a vertical component of 2. Well, actually, it's not quite there. It's at 2, 4. So that would be about here, actually. 2, 4. So that's where the object is at time is equal to 2. And here's my velocity vector at time is equal to 2. Horizontal component of 1 and a vertical component of 2. So it will look something like this. So what that tells you is this is the direction in which the object is moving at time is equal to 2. And the magnitude of this vector that I just sketched in green would tell you the speed of the object at time is equal to 2. So if you wanted to find the speed function for this particular object moving in the xy plane, you're going to do speed is the magnitude of the velocity function. So you would have the magnitude of the velocity vector, which is, by definition, the square root of, here's the velocity vector. The horizontal component is the constant function 1, so you have 1 squared, plus the vertical component is the function 2t, so you have 2t squared. So this is a scalar, so you have the square root of 1 plus 2t squared is 4t squared. And if you wanted to evaluate this function at time is equal to 2 to figure out the speed of the object at time is equal to 2, you would have the square root of 1 plus 4 times 2 squared. 2 squared is 4, 4 times 4 is 16, 16 plus 1 is 17. So the speed of the object at that particular time would be exactly square root of 17 units per second. Units per second. So that's how fast the object is going at that particular instant in time. Now we'd like to take a look at how to find the acceleration vector, and it is the derivative of the velocity vector, and the velocity vector is right here. So to find the acceleration vector, all you're going to do is the following. Take the derivative of the horizontal component of the velocity function. The derivative of the constant 1 with respect to t is 0, so you get 0I. And then take the derivative of the vertical component of the velocity function. The derivative of 2t with respect to t is 2. So you get 2j. So this is the acceleration function. It is a vector. It is called the acceleration vector. 0I, you don't have to write that if you don't want to. You can just write 2j. But of course there is a 0I there. So the acceleration vector at time t is equal to 2 would be 2j. And if I wanted to represent that, here's what I would draw. There is no horizontal component of the acceleration, only a vertical component of the acceleration. And it would look something like this. This would be what it would look like. Now, based on the information that I had earlier, we know that the magnitude of the velocity vector is square root of 17, which is a little bit more than 4. So I should have made this a little bit longer. It was because of the inaccuracies in my graphing that it wasn't as long as it needed to have been. But here is the acceleration vector at time is equal to 2. Let's take a quick look at another example. Here's number 3. The instructions are: the position vector r of t describes the path of an object moving in the xy plane. Sketch a graph of the path. Sketch the velocity and acceleration vectors at the given point. So the first thing that you want to do is make a table where you have t and r of t. So you can choose different values for t, like -2, -1, 0, 1, and 2. And for each value of t, you'll get a position vector, which I will write in component form. The last one is for t is equal to 2. So when t is -2, I have -2 squared is 4 and -2. When t is -1, I have 1 and 1. When t is 0, I have 0, 0. When t is 1, I have 1, 1. When t is 2, I have 4, 1. And with this, I can sketch the path of the object moving in the xy plane. So this one is 4, 2 here, not 4, 1. So now we can plot each of these points. I have 4, -2. Of course, you can draw the vectors in standard position, and these would be the terminal points of the vectors, telling us where the object is at a particular instant in time. And so the object is traveling along this path, having this orientation. And what we like to do is for the position vector r, describe the path of the position vector r describes the path of an object moving in the xy plane. Sketch a graph of the path. We've already done that. And sketch the velocity and acceleration vectors at the given point. So if you look at the given point, it is 4, 2. The given point corresponds to time is equal to 2. So what we need to do is we need to find the velocity and acceleration vectors and evaluate each one at time is equal to 2 to get a velocity vector for time is equal to 2 and sketch it, and then to get the acceleration vector for time is equal to 2 and sketch it. So the velocity vector is found by differentiating each component of the position vector. So the derivative of t squared is 2t, so I have 2ti. And the derivative of t with respect to t is 1, so I have 1j. And the acceleration vector would be the derivative of 2t with respect to t is 2, and the derivative of 1 with respect to t is 0. So I have 2i plus 0j. And if I evaluate the velocity vector at time is equal to 2, I get 2 times 2 is 4, 4i plus 1j, and I get the acceleration vector at time is equal to 2 would be 2i plus 0j. And I can now sketch the velocity vector at the point 4, 2. I will start with the initial point of my velocity vector at the point 4, 2, and the velocity vector has a horizontal component of 4 and a vertical component of 1. So the red vector that I just sketched, it represents the velocity of the object at time t is equal to 2. The object is moving in the direction shown by the vector, and the speed of the object would be equal to the magnitude of this vector, or the length of this vector. And if I were to sketch the acceleration vector at time is equal to 2, I would have 2i plus 0j. There is no vertical component. This would be the acceleration vector at time is equal to 2. There is only a horizontal component of acceleration and no vertical component of acceleration. Let's take a look at number 9. The instructions are: the position vector r describes the path of an object moving in space. Find the velocity, speed, and acceleration of the object. You can take a look at what we have here. For motion along a space curve, the definitions are similar to motion along a plane curve. That is, if you have a position vector with an extra component for the third dimension, and each of the standard unit vectors I, j, and k would be as follows. I would be 1, 0, 0. J would be 0, 1, 0. And k would be 0, 0, 1. Now we're talking about a curve in 3 dimensions. So we would have the xy plane as you see there, and then there's now we go into 3-dimensional space with the introduction of the z-axis, which is perpendicular to the xy plane. So, and the standard unit vectors I, j, and k would be, I would be 1, 0, 0. It would look like this. J would be 0, 1, 0. It would look like this. And k would be 0, 0, 1, and it would look like this. But aside from that, everything else is the same as what you just saw with plane vectors. For motion along a space curve, the definitions are similar. If you have the position vector r of t, and you have these 3 component functions, which are real valued functions, the velocity vector is the derivative of the position vector. You would take the derivative of each component. The acceleration is the second derivative of the position. You would take the second derivative of each component function. And the speed is the magnitude of the velocity. You're just going to take the square root of the sum of the squares of the component functions for the velocity. So now we'll take a look at number 9. This is the position vector. Find the velocity, acceleration, and speed of the object. So the velocity is just the derivative of the position. So take the derivative of each component function with respect to t. So I get 1i here plus 2j plus 3k. And then the acceleration would be the derivative of the velocity, and I would get each of my component functions for velocity are constant functions, so the acceleration would be the 0 vector. And if you wanted to find the speed, you need to find the magnitude of the velocity, which would be in our case, for this particular problem, the speed would be a constant speed for all times, and it would be the square root of 1 plus 4 plus 9. 1 plus 4 plus 9 is 14, and that would be a constant speed. Now we'd like to conclude our lesson by taking a look at a problem where you are given an acceleration function with some initial conditions, and you're being asked to find the position function, and then once you have the position function, to find the position of the object at a particular time. So let's look at an example for this. Before we look at the example, just make sure you understand that in the previous examples that we looked at, we began with a position function, which we differentiated to get the velocity function, which we differentiated to get the acceleration function. In this problem, we begin with the acceleration function, so we have to find antiderivative of the acceleration function, which would give us a velocity function with constant vector of integration. And then we have to find the particular values of the constant that would satisfy whatever initial conditions we have for velocity. And then we would have to find the antiderivative of the velocity function, which would give us a position function with a constant vector. And then we have to find the particular value of that constant vector, which would satisfy the given initial conditions for the position function. So that's the problem that we want to look at now. We're given the acceleration function, and we want to use that to find the position and to find the velocity function first, the velocity vector first, and then the position vector, and we would use the given initial conditions to help us do that, and then we will find the position at time is equal to 2. And the reason why I still have this here is just to help you understand that since acceleration is the derivative of velocity, velocity is the antiderivative of acceleration, and since velocity is the derivative of position, position is the antiderivative of velocity. This is the problem that we will conclude our lesson with. An object starts from rest. So look at these words. An object starts from rest, meaning when it starts moving from rest, which means at time is equal to 0, the object was at rest, meaning it was not moving. So we actually have an initial condition from those three words, starts from rest. The initial velocity is the 0 vector. So we have 0i plus 0j plus 0k for the initial velocity vector. An object starts from rest at the point p1 to 0. So this is also an initial condition. This is the initial position of the object. So r of 0 is 1i plus 2j plus 0k. So we have some initial conditions. These are initial conditions. So having identified the initial conditions, let's read on. An object starts from rest at the point p(1,2,0) and moves with an acceleration of, given by this acceleration function. A of t is equal to 1j plus 2k. You don't see an I component, so that means the I component is 0. So you can write 0I plus 1j plus 2k. So an object starts from rest at the point p(1,2,0) and moves with an acceleration of A of t is equal to 0I plus 1j plus 2k, where the magnitude of the acceleration vector is measured in feet per second per second. Find the position of the object at time is equal to 2 seconds. So to do that, to find the position of the object at time is equal to 2 seconds, we have to begin by finding the position function, and once we have the position function, we can evaluate the position function at time is equal to 2 seconds. So per our discussion from earlier, we will begin by finding the antiderivative of the acceleration function, which would give us our velocity function. And then we have to use the initial conditions that are given for the velocity at time is equal to 0 to find what the constants of integration should be for each of our component functions. So let's go ahead and do that. So the velocity is the indefinite integral of the acceleration function. So we will have the indefinite integral of 0 with respect to t multiplied by the standard unit vector I, the indefinite integral of 1 with respect to t multiplied by the standard unit vector j, plus the indefinite integral of 2 with respect to t multiplied by the standard unit vector k. And what would be an antiderivative of 0? It would just be some constant. The derivative of any constant is 0. So you'll have c sub 1 I. And then here I would have an antiderivative of 1 with respect to t would be t. The derivative of t with respect to t is 1, plus a constant of integration c sub 2 multiplied by the standard unit vector j, and an antiderivative of 2 with respect to t would be 2t. The derivative of 2t with respect to t would be 2, plus a constant of integration c sub 3, and that's going to be multiplied by the standard unit vector k. My next step, which I will show here to try to keep everything on the same screen, is as follows. I have the velocity function at t. I have an initial condition for the velocity at t is equal to 0. So I'm going to take this function that I just found and evaluate that at t is equal to 0. So that would just give me c sub 1 I, there's no t there, right? And then I substitute 0 for t, and that would give me 0 plus c sub 2, or c sub 2j. And then I substitute 0 for t here. 2 times 0 is 0, so I have c sub 3k. My objective here is to find the values of these three constants, c sub 1, c sub 2, and c sub 3. This is the velocity vector evaluated at time is equal to 0, the velocity vector that I had just found, by integrating the acceleration vector with respective constants of integration for each of the component functions. And now I'm trying to figure out what these constants of integration should be so that this initial condition for the velocity vector at time is equal to 0 would be satisfied. So I evaluated my velocity vector that I had found at t is equal to 0, and this is what I came up with. And now I would like to equate that with the initial condition that's given for the velocity vector at time is equal to 0. Now, when I equate those two vectors, the corresponding components must be equal. So C sub 1 must be equal to 0, C sub 2 must be equal to 0, and C sub 3 must be equal to 0. So I now know my velocity vector. Each of those constants of integration are all 0. So we have the velocity vector, which I will write now in gold as a function of time, would be C is 0, so I have C sub 1 is 0, so I have 0I. C sub 2 is 0, so I have t plus 0, or just tj. And C sub 3 is 0, so I have 2t plus 0, or just 2tk. So this is my velocity vector. What am I going to do with this? I need to integrate this again to get my position vector, which will have constants of integration for each of my 3 component functions, and I will have to repeat the process that you just saw to figure out what the values of those constants should be so that this initial condition for the position will be satisfied. So to complete the problem, we have to find r of t, the position vector, and evaluate that at t is equal to 2. So let's go ahead and take what we just found, the velocity vector, and integrate that to find our position vector. So we're going to integrate on a component by component basis. So we have 0, the indefinite integral of 0t, the indefinite integral of 0 with respect to t, multiplied by the standard unit vector I, the indefinite integral of t with respect to t, multiplied by the standard unit vector j, and the indefinite integral of 2t with respect to t, multiplied by the standard unit vector k. So for the first case, we're going to have a constant for our antiderivative because the derivative of a constant will give us 0. And I used C sub 4 because I had used C sub 1, C sub 2, and C sub 3 earlier in my problem. So C sub 4, I, and then for the second component, I have the derivative of, the antiderivative of t with respect to t would be t squared over 2. When you differentiate t squared over 2 with respect to t, you get t, plus a constant of integration, c sub 5, multiplied by the standard unit vector j. And then for the antiderivative of 2t, I will just get t squared. The derivative of t squared with respect to t would be 2t, plus a constant of integration that I call c sub 5, multiply that by the standard unit vector k. So now, what do I need to do? I need to figure out what r of t is. And to figure out what r of t is, I need to figure out the values of these constants. And to figure out what those values are, I'm going to use my initial condition, r of 0, but I need to evaluate what I have at t is equal to 0 to allow me to use this, because this is r of 0. So I'm going to evaluate r at t is equal to 0, and when I do that, there is no t here, so I just get c sub 4i. Wherever I see t, I will substitute 0, so that just gives me c sub 5j. And then wherever I see t, I will substitute 0, so that just gives me c sub 6k. And now I have to equate what I have here to my initial condition, because these are both r of 0, and the only way these two vectors can be equal is if corresponding components are equal. So c sub 4 has to equal 1. C sub 5 has to equal 2. And c sub 6 has to equal 0. So now I have found my vector-valued function for the position of my object at time t. And I will go ahead and write that here. R of t is going to be equal to 1i, c sub 4i, plus t squared over 2 plus c sub 5, which is 2, j, plus c sub 6 plus t squared plus c sub 6k. C sub 6 is 0, so I just have t squared plus 0, or t squared k. That's the position function. And the last thing that I need to do is find r of 2. What was the position of the object at time is equal to 2? So now that I have the position function, I just need to evaluate that at time is equal to 2, and I get substitute 2 wherever you see t. So I have 1i, 2 squared is 4, 4 divided by 2 is 2, 2 plus 2 is 4, so I have 4j, and then 2 squared is 4, so 4k. So that is the position of the object at time is equal to 2. 1, 4, 4. So today we looked at, given a vector-valued function for the position of a particle moving in the plane, you'll be able to find vector-valued functions for the particle's velocity and acceleration, and find a real-valued function for the particle's speed. And the last example that we looked at, we started with an acceleration function and we found antiderivatives. To help us find the position function, we of course used some initial conditions as well that were given. And that will help you to be ready for the next lesson, which we will look at tomorrow, in which we will start with an acceleration function for an object in projectile motion and derive the position function that would tell us the position of the object in projectile motion at a particular time t in terms of some parameters.